control of the accuracy-speed balance in the design of optical systems for augmented and mixed reality devices. Whenever we talk about simulation technology, there is a compromise that is always on the table, which refers to the balance between the accuracy of the results we can obtain through the simulation and the speed with which those results can be generated. What speed means in this context is obvious. It is the inverse of the time that we have to wait between the moment when the simulation starts running and the moment when the results are delivered. And this depends both, obviously, on the hardware we're using as well as on the characteristics of the algorithm. And if we focus on the second side of things, on the algorithm, the speed depends on two numerical parameters. One, the amount of information that the algorithm has to handle, the number of sampling points of a field, for example, or the number of rays of a ray bundle in ray tracing. And two, the number of binary operations that the algorithm in question must perform with that information we just discussed in order to replicate the behavior of the light propagating through the system that is being simulated. Both are coupled. So the more numerous the samples, for example, the more operations a given algorithm will have to perform. But in terms of computational resources, the amount of information is more related to the amount of physical memory that is needed to store that information, and the number of operations is the work of the CPU, or in general, whatever processing unit is being used to run the algorithm. So that also establishes a relationship a little bit between the algorithm and the hardware that we have available. So that's it for the speed. What about the accuracy? What does accuracy mean in the context of optics and optic simulations? Higher accuracy entails more closely replicating physical reality and depends on the mathematical models and algorithms selected to construct the digital twin. Then we need models for different types of sources, different types of components, and different types of detectors in order to construct said digital twin. As is often the case in science, to help our human brains make sense of a chaotic reality, we have classified the phenomena that are relevant in optics into different categories, and we have attached different labels to these effects so that we speak of including aberrations or energy redistribution, diffraction, scattering, interference, speckle, polarization, coherence, or spatial-temporal evolution, among others, in our models. The flexibility that we need to strike that delicate balance between accuracy and efficiency every time, for every simulation, requires having a pool of different techniques at our disposal. So that, for instance, we can choose a model that includes diffraction when we need to include diffraction but not otherwise, or a model that includes temporal coherence when that is relevant but not in other situations. These modeling techniques have to be capable of cooperating, of working together, so that we can build our digital twin by picking and choosing the modeling techniques that make sense for the different parts of a specific system. They will then, together, these modeling techniques produce a result for the whole complex system. And then for a different system, the selection of techniques will be different. And it may even happen that for a single system, the accuracy and speed requirements may change over time, or for different types of measurements, as we're actually going to see in some of the examples. And so a different selection of algorithms will be applicable at different points, even for a single optical system. And so it is that we have covered all the keywords of this webinar, striking the very delicate balance between accuracy and speed that is always a part of working with simulation technology, requires having a pool of interoperable modeling techniques at our disposal that provide the flexibility necessary to adjust that balance and strike the right note, even as the system or the conditions change. And that is precisely what the optical modeling and design software Virtual Lab Fusion offers, a pool of interoperable modeling techniques on a single platform, And this, the fact that it's on a single platform, is also important and worthy of note, because there is then no need to export the results and import them into another software platform to get the full result of a system, a process that would become a lot more cumbersome when it comes to simulating strongly non-sequential systems, as is the case for augmented and mixed reality devices. That's it for the part of a presentation that is delivered in the abstract. We will now move on to illustrating our arguments with tangible examples. Although everything we have said so far holds across the board, the field of augmented and mixed reality provides the perfect scenario to discuss these points in detail. Because the optical systems in this field of application are complex systems with complex propagation patterns, where plenty of different effects play a role. And on top of that, the fact that the field itself, the field of application itself, has appeared relatively recently means that as a community we are lacking the established wisdom and intuition that exists in other applications with a longer history, like, for example, lens system design. Very often the novelty of this field of application translates into the optical engineer not automatically knowing beforehand whether the inclusion of one effect or other is relevant for his design, and if so, at what stage it would be relevant. Must it be included in the initial design process already, or would it be enough to gauge its influence and its relevance at a later stage when we're analysing the design in detail? We're going to see examples of this. Next, let us take a look at a typical layout of an AR waveguide and to gauge what mathematical models we need, what algorithms we need to be able to perform a simulation of such a system. Here we have a waveguide with a 1D pupil expansion concept. It's a HoloLens 1 type layout. We're using it as illustration. The argument that we're going to be using would apply to other layouts, to other architectures as well. We're looking at the device from the back or the front. It doesn't really matter. And this is just for one eye. We would have a symmetric replica of it for the other eye. These are the grating regions on the waveguide: the incoupling region, the expansion region, and the outcoupling region. And the digital overlay that we want to superimpose on the image of the real surroundings in the retina of the wearer is generated here in the light engine, where the light emitted by each pixel is collimated into a plane wave with a finite extension, that means with a given aperture, and a different direction of propagation, so that the position of the original pixel in the digital overlay is translated into a direction. As such, the light that will reach the incoupling grating will be composed of a set of truncated plane waves. They will be mutually incoherent because each of them comes from a different pixel. Each of them will have a given bandwidth depending on the type of source that we select. And this set of plane waves will span a range of directions. This range of directions is known as the field of view. Looking at this sketch, we need to find suitable models for free space propagation. This includes propagation in any homogeneous isotropic medium. We need to find a suitable model for gratings. We need to find a suitable model for the surfaces of the waveguide, as well as for the source and the detectors. Let us start with free space propagation. Here we can choose from the following options: the Rayleigh-Sommerfeld integral, which is a rigorous method, and as such, as a rigorous method, it makes no assumptions at all about that stretch of propagation that we're considering simulating. But on the flip side, it produces results very slowly. Moving down the table, we have the Fourier domain techniques, which basically constitute reformulation of the Rayleigh-Sommerfeld integral in the spatial frequency or K domain. And therefore, since it's just a reformulation, these techniques are also rigorous. The speed here is a bit better because we can take advantage of some numerical tricks like the very well-known fast Fourier transform, which drastically reduces the number of binary operations needed in comparison with a pure discretization of the Fourier integral. Now we reach the part of the table that includes approximations, the two we have just mentioned were rigorous approaches, and now we're talking about approximate methods. The Fresnel integral, which assumes paraxial propagation. Here, as is the case with any approximation, and as we will encounter multiple times in the presentation, if the assumptions of the approximation, if the assumptions of a model hold, we can expect high accuracy, otherwise not. In this particular case, if the propagation is indeed paraxial, then the Fresnel integral will provide high accuracy, otherwise not. The same is of course true, albeit for a different set of assumptions about the last entry on the table, geometric propagation. The presumption here is that diffraction does not significantly evolve in the stretch of propagation that is being considered. Now, in the particular case of AR waveguides, MR waveguides, the two reasonable candidates are Fourier domain techniques and geometric propagation, depending on whether the evolution of diffraction inside the waveguide is important or not, and whether it must be considered or not. This is precisely one of those situations that highlights something I mentioned earlier, that we do not yet know the accuracy, we do not yet know how the accuracy speed scales are tilted in this situation. We will analyse it later. Moving on to gratings and the methods that we have available there, we have a similar situation. The techniques available here span the Fourier model method, which you might also know as rigorous coupled wave analysis. This is a rigorous method, as the name itself suggests, for periodic structures. Then we have the thin element approximation, which is accurate for shallow, thin structures with a large period, and the Kogelnik approach, also an approximation which functions well for thick volume gratings under the Bragg condition. Now, the gratings we normally encounter in the field of augmented and mixed reality have small periods, and under these conditions, the speed of the FMM approach, or the RCWA approach, happily increases at the same time as it becomes the only realistic alternative from the point of view of the accuracy, as the assumptions of the other two methods break down. Finally, for the surfaces of a waveguide, we can choose between an S-matrix approach, which assumes ideally plane surfaces, or the local plane interface approximation, or LPIA, which is a local application of the same. In this case, we tend to choose the second one, as it allows us to perform a tolerance analysis of the device with respect to the curvature of the waveguide, for example, which is impossible when we assume ideally plane surfaces, or it's also possible with the LPIA to consider directly curved waveguides from the beginning. So here, without a doubt, we choose the local plane interface approximation for the waveguide surfaces. A last point that is worth mentioning here, is the treatment of the boundaries, the borders between the surfaces of the waveguide and the grating regions. Beams will often fall directly on this boundary, on this border, and interact partially with the waveguide surface and partially with the grating. In the model, when it comes to the modelling techniques, modelling this accurately requires a local application of the corresponding algorithms with a high resolution of that border. Let us take a look at some simulation results now that show just how important these boundaries are, these borders between the regions. Here we have a false colour view of the beam footprints inside the waveguide with a corresponding local polarization ellipses superimposed on top. We started with a linearly polarized plane wave, that is the source that we put into the system. It is clear that when the beam impinges on the boundaries between regions and consequently interacts partially with the surface and partially with the grating region, This can affect the polarization state, creating local variations in the polarization of the light. Next, let us consider and carefully analyze some of those situations where the selection of a modeling algorithm is not fully clear-cut. We put a pin in those earlier on. We already spoke of the free space propagation inside the waveguide and whether the inclusion of diffraction was necessary or not in that case. Another such example that is not clear-cut is temporal coherence. And for this, two options are available. We're talking now about modeling techniques for the source. The rigorous one is to take the wavelength spectrum of the source, sample it so that it's resolved well, and perform one simulation, one pass of the whole system per wavelength sample. The results of the different wavelengths are then combined at the end, with each wavelength mode being fully autocorrelated. That means it's fully capable of interfering with itself, but it is incoherent to all the other modes, all the other wavelength modes, thus mimicking the effects of the finite bandwidth of a stationary source. But we also have an approximate alternative in the time domain that only requires a single pass of the system, rather than, as before, one pass per wavelength sample in the spectrum. This approach, this approximate approach that only requires a single pass, consists of using the central wavelength of the spectrum and tracing its progress through the system, and then the sum of the overlapping beam footprints on the detector is performed coherently, that is, taking into account phase differences, or incoherently, adding squared amplitudes directly regardless of the phase, depending on the difference in travel time between the individual footprints. So it will be done coherently or incoherently, depending on the difference in travel time between the individual footprints and whether that travel time difference falls within or without the coherence time of the original source. This approach evidently neglects dispersion effects in the course of the propagation, which in this type of system may be caused mostly by the dispersive nature of the media involved, as well as by the dispersive nature of grating diffraction. This is why this approach only makes sense when the bandwidth of a source is not too large. But on the flip side, it is much, much faster than the other one, more so the heavier the individual simulations per wavelength happen to be, and the more wavelength samples are needed to resolve the spectrum well, since the total simulation time scales linearly with the number of wavelengths. That is assuming that the simulations per wavelength are carried out sequentially from the computation point of view. But does this trick suffice in the context at hand in terms of the accuracy it can provide? This trick where we just simulate the central wavelength and then some coherently or incoherently, depending on the travel time difference. Does it suffice in this AR-MR context? So, summing up, this leaves us with two open points that we have to clear up. One, the inclusion of diffraction in the propagation inside the waveguide, whether it is relevant or not. And two, the method to simulate finite temporal coherence of the source. In order to be able to reach a conclusion, we first need to know what it is that we want to achieve from a given simulation, what it is we want to measure and characterize. In other words, what is the detector going to calculate? And of particular importance in this field of application are the irradiance in the eye box, with the object of gauging uniformity per FOV mode, and the point spread function and modulation transfer function on the retina of the wearer of the glasses. So that's the next step, to determine the influence of the approaches we're on the fence about regarding diffraction and temporal coherence on these two performance measures, uniformity in the eye box and PSF-MDF. First, diffraction inside the waveguide and uniformity in the eye box. We see here a comparison of the result with and without diffraction. The effect of diffraction is evident in the diffraction ripples that appear around the boundaries between regions in the footprints. But this rippling effect only slightly smears the line separating the regions when it comes to an optimization, for instance, of grating parameters like height and fill factor of a binary profile. It is more than enough to consider the grating response for the central region of each beam. The inclusion of diffraction is then, in this case, unnecessary for this particular process of optimizing grating parameters for uniformity in the eye box. But what about the calculation of the PSF and MTF at the retina of the user? Please note that we're only discussing the inclusion of diffraction for the propagation inside the waveguide. It is a given that diffraction in the final propagation step, where the focal spot is formed on the retina, must be included, because this is a completely diffraction-dominated effect and propagation step. What we're discussing here is the inclusion of diffraction inside the waveguide for the calculation of the PSF-MTF. The admittedly unobtainable ideal that we want to get as close as possible to with our design in terms of PSF-MTF per FOV mode is that of a completely filled eye pupil with uniform irradiance. This would generate a beautiful area pattern on the retina, and here we can also see its Fourier domain counterpart, the MTF, the modulation transfer function. When the eye pupil is only partially filled, the error pattern becomes enlarged, as we can see here, and the MTF indicates that not as many cycles per millimeter as before can be resolved by the system. In AR waveguides, however, the typical situation is much more like this. A set of partial footprints overlapping each other and riddled with boundary effects is what is going to eventually reach the pupil of the eye of the wearer of the glasses. Again, this is per FOV mode. Without diffraction, this is what the PSF and the MTF look like for such a situation. When diffraction is in the waveguide is taken into account, the patterns change considerably, as we can see. And the conclusion is then that when it comes to analysing the PSF and MTF, we do need to include diffraction inside the waveguide. So that settles it for the question about the inclusion of diffraction. So that just leaves us with temporal coherence, and we go back to the MTF for that. On this slide, we see a comparison of the curves for the situations we are envisaging, a comparison of the two models. In blue, for the rigorous Fourier domain variant, where the wavelength spectrum of the source is sampled well and each wavelength sample is traced through the system. And in orange, for the time domain approximation, where we trace a single wavelength mode and then sum the results coherently or incoherently depending on travel time difference. And we see the results for 3 different values of the bandwidth. Evidently, for the ideally monochromatic case, there is no difference between the two approaches since there is a single wavelength point, a single wavelength mode anyway. But in the other 2 cases considered, the accuracy-speed balance speaks mountains in favour of the time domain approximation. On this slide, we have a final rundown of the conclusions we have reached so far through our comparisons. Of course, it goes without saying that all the simulation results we showed were performed using simulation technology in Virtual Lab Fusion. The icing on the cake is that these conclusions are completely validated by experimental measurements, which are the ultimate test always, obtained in the context of a collaboration among the companies you can see listed on the slide. I want to wrap this up by mentioning 2 very exciting developments that we can expect from Virtual Lab Fusion software in the summer of 2023. The full simulation of optical systems for AR and MR entails a huge number of what we can call elementary simulations, a single run of the system for one wavelength, one FOV mode, and a fixed waveguide element, a fixed set of parameters. The modelling of the full FOV requires multiple of these elementary simulations, each of them with a different FOV mode in the source. An optimization process requires, again, multiple passes, each of them with a different set of parameters in the waveguide, times, potentially, the number of FOV modes or wavelengths which may be considered in the design. I'm sure I need not go into a lot more detail as to why the release of a new distributed computing toolbox that helps parallelize the computation of these elementary simulations is good news for anyone working or expecting to work with virtual app fusion in the augmented reality field. Here on screen you can see the results of some tests that reveal the potential of this tool in terms of simulation time. Furthermore, this will come accompanied by the release of an optimization toolbox, which will offer advanced optimization algorithms, an evolutionary algorithm for instance. It is on this exciting note, looking to the promising future developments of virtual app fusion software, that we finish this presentation and open the floor to your questions. Thank you very much for listening.